Hello there, and welcome back. In this video, we're going to continue our discussion of probability theory and random variable theory and its applications into statistical inference for population parameters. In particular, this discussion is going to be focused on creating and analyzing a structure known as a confidence interval, which will allow us to make statistical inferences about the population parameter, the arithmetic mean, mu. So let's just briefly go over a couple of principles that we're going to need that we've actually discussed already. So let's recall that if x is associated to a normal distribution whose mean is mu x and its variance is sigma x squared, then the arithmetic mean, random variable, is also going to be associated to a normal distribution whose mean is the same as the mean of the population that we're sampling from, and the variance is going to be equal to the variance of the original population divided by the sample size, or equivalently the standard deviation of the population, or equivalently the standard deviation of the population divided by the square root of n. Usually we represent parameters of populations based upon the variances because usually the variances have nicer properties than the standard deviation does. So if x is associated to a normal, the averages of those x values will also be associated to a normal, and moreover the z-scores of those averages, which again is going to be the square root of n times mu x bar, so the square root of n times x bar minus mu x all over sigma x, this is going to be associated to a standard normal or a z probability density function. So these are some of the principles that we've actually gone ahead and discussed and their applications in previous discussions. So let's look at a picture to sort of build how this is going to build into the confidence interval approach. So consider the standard normal, or just in general the normal probability density function. So we already know that this distribution is going to be a bell-shaped curve, and we know if this is associated to the random variable x bar, then the sample mean has this type of distribution. So usually we assume that the sample mean that we get, let's assume it's the little x bar, let's assume without loss of generality that it's going to be somewhere in the middle of this distribution, near the mean of the population. So usually what we do in order to construct a estimate for the parameter mu is we build a margin of error around our point estimate x bar, which is the point estimate for mu x. So since this is a point estimate, we need some margin of error in order to construct our decision criteria, in order to say conduct our hypothesis test, because if the claim is significantly larger or significantly less than our point estimate for this value of mu, then we would of course reject the null hypothesis that that is indeed the value. So we need to have some distribution to represent our levels of confidence and our levels of statistical significance in order to come up with that conclusion. So what we usually do is we go to this distribution and we sometimes, not always, but sometimes build a symmetric region around our sample mean with respect to its distribution, which we're assuming is a normal and or standard normal distribution. So these boundaries, let's assume this is the standard normal distribution, is going to have 2 points that are going to define a two-sided alternative hypothesis test. So this lower value is going to be the negative z, what we call the critical value, and this upper boundary is what we call the z critical value. Generally speaking, this is a lower boundary and this is an upper boundary in the case that you do not have symmetric confidence intervals. But generally speaking, if this middle point is 0, that means we're working in the standard normal spectrum. That means this value and that value are the same exact number except just opposite values. So let's just take the simple scenario, the minus z crit to z crit value, such that this area is equal to c. So that's going to correspond to our level of confidence, right? Which again, recall, is the complement of our level of statistical significance, or some people call alpha the type 1 error. So how do we represent this area C with respect to probability statements? So let's just give that a quick write down. So the probability that Z, because this x bar is associated to a Z distribution, is going to fall between these two numbers Z crit and positive z crit. Right, so this probability is with respect to the standard normal distribution. So this is equal to C. And again, an equivalent way of writing this probability statement, since we're on equal sides, is the probability that the absolute value of Z is less than the positive Z critical value. And again, another way of representing this instead of C is going to be 1 minus alpha. So we have this particular statement or this particular statement, whichever one you prefer. They are equivalent, but they say the same exact thing. So the probability that a z random variable lies between these two z critical values is equal to our level of confidence. So what variables are associated to a z distribution? So remember, if x is associated to a normal distribution, that means x bar is associated to a normal distribution. That means the z-score for these averages is associated to a standard normal distribution. So one particular variable that is associated to a z distribution or a normal distribution is going to be the z-score for the population mean, the z-score for a sample mean, which is x bar. So what is the z-score for a sample mean? So remember, the z-score for the sample mean is going to be equal to the square root of n times x bar minus mu divided by sigma, where mu and sigma are the mean and standard deviation of the population that we're sampling from. So that means this statement that we have constructed here is equivalent to writing the probability that the absolute value of the square root of n of x bar minus mu x divided by sigma x is less than the z critical value is also equal to c. Now let's just look at this statement just in a little bit more detail, because there are definitely a few things that we can sort of simplify or make this statement a little bit more nicer. Firstly, the standard deviation is always a positive number, so the absolute value of sigma is going to be equal to sigma. The square root of n also is a positive number, therefore the absolute value of square root of n is just the square root of n. So we can write this as the probability of the square root of n over sigma x times the absolute value of x bar minus mu x is less than z critical value is going to be equal to our level of confidence. Now, since this object is a positive number, I can actually multiply both sides of this object, of this inequality, both sides, and my inequality sign is not going to change direction because this is a positive number. That's going to give us the probability that the distance between x bar and mu x, or the mean, is less than z critical value times sigma x divided by the square root of n is going to be equal to c. Now, this type of statement we've actually seen a lot of, especially when we were talking about approximations to probabilities, for example, the empirical rule, Chebyshev's inequality, and things related to that, because we're looking at the distance between a particular number and a particular value, right? And in particular, this value is a sample mean. So since this is an inequality, we can rearrange this in terms of non-absolute value inequalities. So this is going to be equivalent to what? So this is going to be the same as the probability that x bar minus mu x is between two values. So what are those two values going to be? So it's going to be equal to minus z critical value times sigma x over the square root of n, and it's positive z critical value times sigma x over the square root of n. That's going to be equal to c. And then let's actually solve for mu x here, because we actually don't know what mu x is, and we can always get values for the x bar by sampling. So I'm going to subtract both sides of this inequality by x bar. What is that going to give us? So that's going to give us the probability that negative x bar minus z crit times sigma x over the square root of n is less than negative mu x is less than negative x bar plus z critical value sigma x over the square root of n is going to be equal to c. And now what I'm going to do is I'm going to multiply all sides of this inequality by negative 1. When I do that, my inequality signs are going to reverse in the other direction. So that means this side becomes the left and this side becomes the right. This sign is going to be positive, that's going to become negative. This sign is going to become positive, and that sign is going to become positive. So what are we going to have there? So we're going to have the probability that mu x is between x bar minus z crit times sigma x over the square root of n. So that's this object just reversed. and then x bar plus z crit times sigma x over the square root of m. The probability that this is true is equal to c. So, what exactly do we have here? So notice that we have almost a symmetric relationship on these boundary sides of mu x. So what do we have? So let's actually define this object here, because this actually looks like our margin of error, or at least a good choice for a margin of error, right? So define the margin of error, let's call it epsilon, to be equal to this z critical value times sigma x over the square root of n. Now, why is this a good choice for the margin of error? Well, remember what margin of error should include. It includes some representation of our level of confidence, and it includes our standard error associated to the estimate, which that indeed is, right? So that's the standard error associated to x bar, this sigma x over the square root of n. So therefore, our probability statement can be rewritten as x bar minus epsilon is less than mu x less than x bar plus epsilon is equal to c. Now, I just want to make this very, very clear. The random variable in this probability statement is x bar. So that is our random variable. Our random variable is not mu x. So this does not say the probability that the mean of the population is in between these two values is equal to c is not true. Because remember, we technically have control over this value of c, which means we would have control over the probability of where mu is. That doesn't make sense. So this says the probability that x bar satisfies this relationship is true, but it doesn't say the probability that mu x satisfies this relationship is true, because remember, mu x is fixed, c is dynamic, x bar is a variable, therefore make sure you get your concept straight associated to that, because since mu x is not a random variable, this is not a probability about mu. It just involves mu. So what is this statement that we've actually constructed, and what is its purpose? So this is what we refer to as a confidence interval for the population mean. Confidence interval for the population mean mu. So we usually write this confidence interval for the population mean mu. So our level of confidence is usually superscripted, and the subscript on CI usually represents the parameter that we're estimating, is going to be equal to x bar minus epsilon and x bar plus epsilon. So that's our confidence interval. So that's cool. So what is this epsilon? Let's just review what that is. So the margin of error for this is going to be equal to z critical value times sigma x over the square root of m, or equivalently, the margin of error is equal to the z critical value times the standard error of the estimate of using x bar as an estimate for the population mean mu. So these two things and perspectives are equivalent, but using this latter one, that gives you a little bit more flexibility over what you choose the standard error of x bar to be, because sometimes we know a couple other bits of information such as the population size. What if we don't know sigma? Then we can sort of change our standard error formula. But this is the general formula for the confidence interval for the population mean mu. So now let us take a moment and go through a few examples on how to actually construct this confidence interval mu, and also how to apply it to hypothesis testing. So let's start off with a very basic example. Let us assume we have a population P that is normally distributed, and let's assume that we know the population standard deviation sigma to be 5.7. So in this case, we do not know what the population mean mu is. Let's then go ahead and select a simple random sample S from this population, and let's assume that the arithmetic mean of that sample is 8.3, and the size of that sample is 24. Let us now construct a 92% confidence interval for the population mean mu. So how do we go about solving this? So to begin, we need to find our critical value. So since P is normal, that means the distribution of our sampling mean, or the sampling distribution of sample means, is also going to be normally distributed as well. If P was not normal, it's possible that we can use the central limit theorem to justify that the distribution of x bar is approximately normal, but of course there's some error that we sort of need to anticipate or think about when we start to justify our conclusions. So since this is our distribution of x bar, then we're going to be looking for, let's assume, a two-sided level of confidence, such that the area in between these two values is equal to c. We want C to be equal to 92%, so therefore we need to find these boundary points. Remember that this lower value is the 1 minus C over 2th percentile, and this upper boundary is the 1 plus C over 2th percentile, and we've actually discussed these different types of properties and how to find them previously. So if this is indeed a Z or a standard normal distribution, you should be able to find that the Z critical value for a 92% level of confidence, in particular we're looking for the 1 plus C over 2th percentile, is going to be equal to 1.7507. The reason we only find the upper boundary is because if we assume that these two tails are equivalently distributed, that means 1 minus C over 2th percentile of the Z distribution is just going to be negative 1.7507. So as long as we're working in a two-tailed distribution where the tails are symmetrically distributed, we technically only need to find the upper one, in particular the positive one. Now that we have our critical value, which is associated to a 92% confidence interval, now we need to figure out the standard error associated to the estimate of using x bar as an estimate for mu x. So what is that going to be? Well, with all of the information provided, the standard error of the estimate associated to using x bar as an estimate for mu x is going to be equal to sigma x divided by the square root of n. Keep in mind, this formula came from the variance of the random variable x bar. Take the square root of that. So once we have sigma x and square root of n, which we have both of those numbers, that's just going to be equal to 5.7 divided by the square root of the sample size of 24, which is going to come out to approximately 1.1635. So that's our standard error. The next thing that we need to calculate is the margin of error for our confidence interval. So remember, the margin of error is going to be equal to the critical value times the standard error associated to our estimate. So once we do 1.7507, so that's an approximation of course, times 1.1635, you're going to get a margin of error of approximately 2.0369. So once we have our margin of error, now we can construct our confidence interval provided that we have our point estimate, which is going to be x bar. So that means the confidence interval, and what confidence interval percentage are we working with? I think 92% we said, for the population mean mu, is going to be equal to, remember, x bar minus epsilon, x bar plus epsilon. The reason we're using x bar is because we're using x bar as a point estimate for mu. It's possible that you may want to choose the median as a point estimate for mu. There's nothing wrong with that, because remember, the median is less skewed or influenced by outliers compared to the mean. So you could have a median-based confidence interval for the population mean. There's nothing wrong with that, of course. So since we actually do know the sample mean for our sample, that's going to give us 8.3 minus this margin of error, 8.3 plus our margin of error. Once we work out those calculations, you're going to get a confidence interval of 6.26 and 10.34. So this is our 92% confidence interval for mu. So I am 92% confident, based upon the sample that I have collected, that the population mean mu is in between 6.26 and 10.34. Remember, that is not the same, so that does not imply that the probability that mu is in between 6.26 and 10.34, it does not imply that this is equal to 92%, right? Because keep in mind, the random variable was x bar, not mu. So please do not confuse those things. Because if our sample changes, that means this confidence interval is going to change. And just because our confidence interval changes doesn't mean that our population mean has changed. Now, one could discuss, well, what if our population mean actually is changing? Is this then a probability statement? We can discuss that later, but that's something that you might want to think about, at least for now. So how does this relate to hypothesis testing? Well, let's assume we're working with a null hypothesis that the mu claim is equal to 12, and since we're working with a two-sided confidence interval, that means our alternative hypothesis should also be two-sided. They usually go hand in hand. So the claimed value of mu is 12, right? So mu 0 is equal to 12. And does 12 belong to this confidence interval? The answer is no. That means we have evidence to believe that the actual population mean mu is actually not equal to 12, in particular something lower than it. So therefore, since the claimed value of mu, which is 12, does not belong to our confidence interval, then I'm going to, would I reject or fail to reject the null hypothesis? In this particular scenario, I would reject the null hypothesis because I have evidence to believe that the population mean mu value is actually less than 12. Okay, so that's how you would apply this to hypothesis testing. So let's look at another scenario that you may encounter. So that's scenario 1. Let's look at scenario 2. Let's assume another person comes up to you and says, okay, well, what I believe that the mu value is equal to 9. So the alternative would, of course, be mu is not equal to 9. That's the general case. So would we reject or fail to reject the null hypothesis in this case? So remember our confidence interval was 626 up to 1034. So 9 is definitely in that interval. So in this particular scenario, we say since the claimed value of mu, which is equal to 9, is in our confidence interval, in particular our 92% confidence interval, then we're going to fail to reject the null hypothesis. Now, if you, of course, choose to accept the null hypothesis, that's okay, I guess, but generally speaking, just because your sample agrees with the claim does not necessarily mean the claim is right. So it's usually safer just to fail to reject the null hypothesis versus accepting it. Now that we have just a basic understanding of how to construct confidence intervals, let's look at a couple other scenarios of confidence intervals for the population mean mu that you definitely probably will encounter in practice. Let's consider this scenario. Let us suppose that P again is a normal distribution with a known standard deviation of 7.3, and let's now also assume that we actually know the population size to be 43. Let's collect a simple random sample S from this population P, where the sample mean of the sample is 13.7, the sample standard deviation is 6.5, and the sample size is 32. Construct a 94% confidence interval for the population mean mu. So how would we go about this? So the very first thing is to construct our confidence interval, starting with the critical value. So again, since we're sampling from a normal distribution, the distribution associated to x bar will also be normal. So we can use a standard normal distribution in order to construct our confidence interval by finding the critical value associated to it. So the z critical value is again going to be the 1 plus c over 2th percentile for the standard normal distribution, where we want this area c to be equal to 94%. Once you actually work out the percentile calculations, you should be able to find that the critical value for a 94% confidence interval is going to be approximately equal to 1.8808. Once you have that particular number, now we need to construct our standard error of the estimate associated to using x bar as an estimate for mu x. So what is that going to be? So the standard error of the estimate associated to using x bar is going to be equal to sigma divided by the square root of n. But keep in mind, we know what capital N should be. We actually know what capital N is, actually. So if our sample size is equal to the population size, then we would hope that the standard error of the estimate associated to using x bar as an estimate from mu should be equal to 0. So in order to accommodate for this fact, what we need to do is include what we call the finite population correction factor, or FPC for short. So this is the FPC, or the finite population correction factor. So you always include the finite population correction factor if capital N, the population size, is known to us. All right, so since we know the population size to be 43, that means we can include the FPC in order to make our calculations a little bit more accurate. So that means the standard error associated to using x bar as an approximation for mu is going to be equal to the standard deviation of the population divided by the square root of the sample size 32 times the square root of the population size minus the sample size all over the population size minus 1. Once you actually work out these calculations, you're going to have 0.6604. Now, I invite you to compare this to the standard error of the estimate associated to using x bar as an approximation for mu. If you were not to include the finite population correction factor, one property of the FPC is that this number always is in between 0 and 1. Therefore, it's always going to make this number a little bit smaller than it used to be. So FPCs make our confidence interval a little bit more smaller, which is actually a good thing in this case. Once we have our critical value and our standard error of the estimate, what is the next thing that we're going to be able to find? So from here we can find our margin of error for our confidence interval, which again is going to be equal to the z critical value times the standard of the estimate associated to using x bar for mu. And once you find this, you're going to find that that's approximately equal to 1.2421. So that's z critical value times standard error. Once we have these two objects, then we can construct our confidence interval. So again, this is going to be a 94% confidence interval for the population mean mu, which is always going to be equal to point estimate, our x bar, minus our margin of error, point estimate x bar, plus margin of error, which is going to come out to finally 12.46, 14.94. So that is our 94% confidence interval for population mean mu. So what are we going to do with this? So let's assume, as an example, if our null hypothesis claim was that mu is equal to 15, and let's assume that we're working with a two-sided alternative that mu is not equal to 15. So if this is the case, we need to say, well, what about this claim? So the claim value of mu, which is going to be equal to 15, does not lie within our confidence interval. So since this is true, the claim is not in our confidence interval, then we're going to be rejecting the null hypothesis, because we have evidence to believe that the true population mean is actually less than 15. Now, it's very important to notice that the boundary point for the confidence interval is actually subjectively close to 15. So some people may append the statement with weak evidence, right? Because the boundary point and the value of 14.94 are practically equal to each other, right? So you would probably have some threshold in order to determine what do you mean by weak evidence versus strong evidence. That's another discussion for another day, but do keep in mind and keep these things in the back of your mind when you're actually coming up with conclusions in regards to this. In practice, some people usually construct the confidence interval or other things such as p-values and test statistics, and then allow the reader to determine whether they should reject or fail to reject, because this thing is of course subjective and usually depends solely on the application that you're actually studying. So let's look at another example of something a little bit more realistic, because notice for all of these things, we're actually assuming that we know the population's standard deviation. Generally speaking, we do not. So how do we tailor our confidence intervals in that scenario? Let's assume that the sample S is drawn from a normally distributed population P, where the sample mean comes out to 26.5, the sample standard deviation comes out to 4.8, and the sample size was 25. How are we going to go about constructing a 97% confidence interval for the population mean mu with these particular assumptions given to us? So again, keep in mind we are given that the population is normally distributed. So it is at least fact that the distribution associated to x bar will be associated to a standard normal distribution for the z-scores and normal distribution for the actual average values. So us going and creating this picture is not a bad place to start. So we want this area to be 97%. Now, we have a couple issues though. We actually don't know what sigma is. So sigma is not given. That means the z-score, which is usually given by the square root of m, x bar minus mu all over sigma, cannot be used, because remember this was associated to a z distribution. So remember, if we don't have sigma, the best thing that we can do is use s, the standard deviation of the sample, as an approximation. So remember, that means we have to switch this score into this world. So this is again a random variable, s, because we technically don't know what the sample standard deviation is going to be until we actually grab our sample. So this is what we referred to as a t-score for the sample mean x bar, which is associated to a t distribution with degrees of freedom, sample size minus 1. Right? So this graph, although still bell-shaped, is a t distribution with a degrees of freedom of sample size, which is 25, minus 1, which is going to be 24. So that's a TV equals 24 distribution. So again, this upper bound is going to be the 1 plus c over 2th percentile of a t distribution with 24 degrees of freedom. And again, this is not called a z critical value, it's going to be called a t critical value. Right? So this is going to give us our t critical value. So if we let v be equal to 24 and we find the 1 plus c over 2th percentile of the t distribution, one should be able to find that the t critical value for this particular scenario is 2.3069. Now, if we were not given the assumption that the distribution was normal, then we can of course assume that x bar is associated to a normal, which again would imply that this t-score value is not associated to a t distribution. We could use this as an approximation possibly, but you should be very careful on your analysis and conclusions. So since we have that, well, what do we have? So now we need to calculate our standard error of the estimate associated to x bar. So the standard error associated to using x bar as an estimate for mu is going to be equal to usually sigma over the square root of n. But sigma over the square root of n is not able to be used here, so that means we need to be using the s over the square root of n alternative. Now, is this okay? The answer is yes, because we're using a t-critical value to approximate this. So everything is okay. So that means this is going to be equal to 4.8 divided by the square root of our sample size, which is actually 25. So we can actually carry this calculation out a little bit more before actually getting our value. But the standard error associated to x bar is going to be 0.96. Now, if we were to actually know the population size, then this would switch into s over the square root of n times the square root of n minus n over n minus 1. That is the normal standard error times the FPC. But we don't know capital N here, therefore we cannot use this particular artifact. Once we have our critical value, which we do have, and we have our standard error associated with the estimate, which we now have, now we can calculate the margin of error for our confidence interval. So our margin of error is going to be equal to the t critical value times the standard error of the estimate associated to using x bar as an estimate for mu, and that's going to come out to approximately 2.2146. Once you have your margin of error for your confidence interval, then you can actually calculate your confidence interval. So the confidence interval that we're working under is a 97% confidence interval, and we're approximating mu. So that's going to be equal to the point estimate, which is x bar minus epsilon, and then our point estimate, 26.5 plus epsilon. And that's going to come out to approximately 24.29, 28.71. So that is our confidence interval that we aim to get. Now, how are we going to use this for hypothesis testing? So let's assume that the claimed value of mu was 27, and therefore let's also assume that we're using a two-sided alternative, in particular mu is not equal to 24. So since we're using a two-sided alternative, that gives us that picture of a two-sided level of confidence. So since the claimed value of mu, which is 24, does this lie in the confidence interval? No. So it does not belong to our 97% confidence interval. Therefore, will we reject or fail to reject the null hypothesis? So since this value is slightly below the lower boundary, we're going to be rejecting the null hypothesis. So reject the null hypothesis, and of course you could say with weak evidence, as long as you have some tolerance level on what do you mean by weak and far. Because remember, the point estimate, 26.5, already is in the exact middle of this distribution. So 24 already is statistically significantly far from 26.5. So you including a threshold is sort of giving even more wiggle room for discussion. But it really depends on the application whether you would want to do that or not. So another scenario, so that's of course scenario 1. Let's do another scenario. Let's assume that the null hypothesis was that mu is equal to 27. So two-sided alternative, mu is not equal to 27. So what would we say here? So since the claimed value of mu, which is 27, would belong to our confidence interval, right? That means our evidence agrees with their claim. That means we're going to be failing to reject the null hypothesis. And if the value 27 is really close to our point estimate of 26.5, and you can argue that with yourself if you want to, then you can talk about the strength of that evidence that you have. Again, fail to reject the null hypothesis is not the same as accepting, but you may, if you choose, accept the null hypothesis. Because sometimes you need to make decisions based upon these claims, so it really depends on the conversation at hand. Anyway, that's just an introduction to confidence intervals for the population mean and its connection to hypothesis testing. Now, there are a couple other alternative ways that you can actually conduct a hypothesis test via what we call test statistics and p-values. We're going to be looking at them in the next discussion. So I hope to see you there. Take care.